Guys, this is an example of a two-way ANOVA, actually a thorough example of a two-way ANOVA. What I really want you to be aware of in this video, I'm going to give you two examples. First of all, I've got a very small data set that I'm going to illustrate how to take it in the form that we typically begin in a two-way ANOVA, how to move it into Excel, convert it into R, and so on and so forth. And then I'm going to provide kind of a real-life example. And this is going to be kind of cool because I haven't worked this one. I know the data set I want to work with, but I haven't. I don't even know what I'm going to do yet. I'll be perfectly honest with you. But there's one data set that's built into R that's got a lot of stuff going on. And I think that we can look at that and design a two-way ANOVA from that data set. If we can't, we'll just we'll get out of class early, I guess you would say. Guys, what I want you to know about two-way ANOVA, it's really just an extension on what we've done with ANOVA. What we do here is, instead of having one independent variable or one categorical predictor, and from the earlier video that I put up, you can see that regression and ANOVA, when you get into categorical predictors, are essentially telling you the same thing. But anyway, a two-way ANOVA, we just add one independent variable or a categorical predictor. So at the end of the day, what two-way ANOVA allows us to do, it allows us to explain more variance. And what I hope you know by now is, I hope you know that the total variance can always be explained by taking, or I'm sorry, can be partitioned out as the sum of the explained variance plus the unexplained, let's put the L there, variance. And in a standard ANOVA, the explained variance is the variance that we explain through, for example, a factor A. But in a two-way ANOVA, we can partition out the explained variance into the variance that's explained by factor A plus the variance that's explained by factor B. And of course, as we've seen before, sometimes there's this kind of overlap between factor A and factor B, where we have a variance of the interaction of the two. So essentially, the explained variance in the two-way ANOVA has to do with the variance that we can explain from factor A plus the variance that we can explain from factor B plus the variance component that we get from the interaction between A and B. Now, the first example I give you, I don't know how it's going to turn out, but I've got the data set up and we can work through it together. But the next example, the one we're going to go on the fly, which I think is actually going to be kind of cool. We'll go through assumptions and a complete and thorough example. The reason I want to give you the real the illustration where I give you the data in the form that's usually collected is it's typically a problem or a mistake that students make in taking the raw data and putting it into a form where R will understand it. So that's the reason for that. So guys, anyway, ANOVA is the procedure that we build on. We can go into a two-way ANOVA, a three-way ANOVA, a four-way, five-way, six-way, and what I would call an N-way ANOVA. Now, these N-way ANOVA designs are just called factorial ANOVA, and not to be confused with something that we're going to call factor analysis coming up here in a few weeks, which is completely different than factorial ANOVA. Factorial ANOVA just says we have more than one independent variable or more than one categorical predictor. So, guys, I may get into an illustration of a three-way ANOVA. Those things get kind of crazy. Two-way ANOVAs get kind of crazy. I would really question your sanity if you get into a four-way ANOVA. If you get into a situation where you have a quantitative dependent variable and you want to look at the difference in group means over four categorical predictors or four categorical independent variables, let's search for another design other than four-way ANOVA, because those things become almost uninterpretable. Guys, so for this video and getting prepared, what you're going to need R up and running. You'll need Excel, and you're going to need G-Power. And the illustration I use we'll use G-Power version 3.1. If you're if you've upgraded and you've got the super duper G-Power version, then good for you. Okay. So guys, I want to get out of here, and first of all, I just have a generic data set that I want to take a look at. And you'll see down here I've got, looks like I've got it up in just as just a picture, and then I've got the Excel file here. So guys, typically what you do when you collect your data is you take the factors, and you can see here that we have factor A and it has 3 levels, and factor B has 4 levels. Our total cell count, 2 measurements, so we have a balanced design. Guys, I would always recommend a balanced design. And a balanced design just says that your cell counts are all equal. And clearly our total sample size here would be equal to 24. All right, so what I did first of all, and it's a common mistake when we come over to the spreadsheet and import it into R, not to set it up correctly. Now what you got to notice here is we have 3 variables. We have our measurement, we have factor A, and we have factor B. If you want to think about something with a concrete example, think about maybe this would be a GPA, maybe this is gender, and maybe this is over instructor. Maybe we've got 2 or 3 instructors that so instructor A, instructor B, instructor C. Now what I need to do now is I need to put in the factors from which these measurements were collected. And you can see that I read across the row at first. So my first 8 measurements are from factor A1. And I designed it that way because, well, okay. Well, gang, it's not going to let me do that. There's a way that you can do that, but I don't remember what it is. So I'm just going to have to crunch it out. All right, then we've got A2. And I need that to be the next 8 measurements. So that, so what do we have there? We have 1, 2, 3, 4, 5, 6, 7. So I need 1 more. And my next measurements are from A3. And I have my factor A measurements taken care of. Now, what we have to notice in the B measurements is the first 2 came from B1. The next 2 measurements came from B2, next from B3, and the next from B4. Now I'm going to copy and paste that. Whoa. All right, guys, I need another B4 there, don't I? All right, so down to 1.2 came from B4. I'm just going to copy and paste that, hoping nothing goofy happens, and paste that. And so let's just choose a random thing in here. Let's come in at this measurement of 1. Let's just do the 0.7. So I'll come over here and I find a 0.7, and it came from B4 A2, and so I have A2 B4. So it leads me to believe that I do have my coding done correctly. Guys, I'm not going to need this anymore, so I'm going to get rid of that. I'm going to maximize this. I'm going to come in and do a save as. Now I've called this workbook, which is perfectly fine, and I want to save it as comma separated values and go for it. It's going to ask me a bunch of stuff, continue, go on. I'm going to close this down. I don't need to resave it because I've already saved it. Alright, life is good. Alright gang, so on my desktop you can see that I have this workbook. I have this one in XLS form. I'm going to move that one to the trash. I don't need it anymore. All I need is the CSV form. And I also don't need my picture anymore. Okay gang, so we've got the workbook on our desktop, so let's bring it in. I'm going to call it data because I'm creative that way. I'm going to attach my data, and I'm going to look at the data. To be honest with you, I could care less about looking at the data, but as a teaching tool, sometimes it's helpful. All right, the first thing I'd need to do is to take a look at the assumptions. And remember the assumptions of the model of a two-way ANOVA. And I'm not going to check those in this situation, but I'm going to check them in the sort of real-life example. So let me go back over here and bring up okay. So okay, let me get rid of that. Essentially we're going to look at effect size, but just for right now, what I want to do is think about the assumptions. So guys, what's the biggie? Independence. The second one is equal variances. We call that homogeneity of variances. And to think the next thing we need is normality. Again, I'm not going to test these. I have a cell count of 2, so the normality may get a little crazy. And the equal variances, I'm going to skip over that as well. Now, the next thing we would do before carrying out our test is we'd need to set up our null and alternative hypotheses. And guys, we're going to have 3 of those. So our first hypothesis will be that the mean for factor A is mean of factor A2. I tell you what, I don't like the way that's coming out. So let's just call this the mean for A1 is equal to the mean of A2, which is equal to the mean of A3. So our first hypothesis is all about factor A. So really what we're doing in the first null hypothesis is just carrying out a standard ANOVA. Our second null hypothesis is going to be all about factor B. I think there were 4 factors for factor B, and our alternative write that right there. As our third null and alternative hypothesis is that factor B or factor A, however we want to say it, well, let me just put it this way. So there's no interaction effect between factor A and factor B. As you might expect, the alternative, there is an interaction. Between A and B. So guys, when running a two-way ANOVA, as I'll illustrate and as I'll point out many times throughout this video, the first time through it's all about the interaction. That's the first thing that I will look at when I run one of those. So guys, let's see how all this is going to happen. What I'm going to do here is run the ANOVA, and I'm going to call this just my fit, and I'm going to run AOV of my measure over factor A cross factor B. Now this is going to give me my my interaction along with the main effects. So hypotheses 1 and 2 deal with the main effects, and hypothesis number 3 deals with the interaction. So I can type fit, and I really don't get anything that turns me on there. But if I do summary fit, we get more of a standard ANOVA table. Now the very first thing I'm going to look at here is I'm going to look at the interaction, and I'm going to see if we have statistical significance, and we don't. So in this case, what I would do is I would rerun the model, and I would call this fit 2 or whatever you like, and I would run my ANOVA over the measure over factor A plus factor B. So this is going to give me my model not including the interaction effect. So guys, when we run through our model and we see that the interaction effect is not statistically significant, then my attention is going to be on factor A and factor B independent of including the interaction. So what did I do wrong? Oh, I see what happened. You guys are probably sitting there screaming at me, aren't you? When communicating with the machine, guys, it matters. All right, guys. So I run my summary of fit 2, and neither factor A or factor B is statistically significant. So I got a small sample set here. Power is probably extremely low. So really, there's just not. I shouldn't have expected much to happen. But this first example was more about looking at the measurements as they're typically provided in a table, getting that into Excel, converting to a CSV, and running the analysis. So that was really the purpose of this. Now, guys, let's talk about effect size. As I hope you know now, let me. All right, gang, so effect size, it gets a little complicated, but at the end of the day, effect size is just kind of a standardized value, if you will, which allows you to examine the impact or the effect of an independent variable on a dependent variable. And again, it's a standardized measure, so it can be compared from research to research without getting into effects of sample size and things of that nature. If you go to, I provided a link on Blackboard for you, and hopefully you'll realize that you have that, and I've got it up here. And if you go to this, you see that there's a lot of different effect sizes. Cohen's F, Cohen D, omega squared. We're going to get into to eta squared. But the one that we're going to examine right now is Cohen's F. And we're not going to examine that. We're going to examine this Cohen's F. And this is for a one-way ANOVA or ANCOVA. It's going to work for a two-way ANOVA as well. And because essentially we're running one-way ANOVAs, we're just running essentially 3 of them. But pay attention to the thresholds on the small, medium, and large effect. So 0.10, 0.25, and 0.40. So each jump is a 0.15 level. It turns out that the way we calculate the effect size for a two-way ANOVA, if we want the effect for factor A, we're going to take the square root of the number of levels for factor A times the F statistic, the test statistic for that factor, divided by the grand sample size. Factor B, as you would probably imagine, and then the interaction for the effect size for the interaction is just the product of the number of levels for A and B times the value for the test statistic divided by n. So guys, we can go back to R and we can get our effect size, and I'm pretty sure it's going to be very small. So guys, we have the effect for factor A will be the square root of, factor A has 3 levels, so we have 2 times the F value, so 1.775, divided by n, which is 24. So the effect size for A is 0.38. So wow, that's higher than I expected. The effect size for B, the square root of 3 times 1.531 divided by 24. So another large effect. And it seems what's going on when we have a large effect like this, it seems like we just don't have enough power to reject a false null. And we'll take a look at that. So my effect for AB, as I'll call it, is the square root of 2 times 3. Well, I don't know why I did that. Times the test statistic for the interaction effect, which is 0.4, divided by 24. So the effect size for AB is 0.31. Now let's just let's get out of here and remember that the effect size for the interaction is 0.32, and I'm going to write that down because I'll forget it. So guys, what I can do now is I can pull up G power and see what kind of power I've got. So first thing I need to do is choose the appropriate test family, and ANOVAs run off the F distribution. And the next thing I need to do is run main effects and interactions. So actually I had what I needed. Now when I come down here, my effect size for the interaction, it's kind of cool that if you put your cursor over there, it'll give you the thresholds for small, medium, large using Cohen's F. The effect size that we have is 0.32. I want a 0.05 type 1 error rate. My total sample size was 24. The degrees of freedom for the numerator, in this case, this is going to be a minus 1 times b minus 1, so this is going to be 6. And the number of groups, we have 4 levels for factor, well, I forgot, we have A1, A2, A3, so we have 12 total factors, okay? Now, when I calculate my power, I'm expecting a really low power, and it actually turns out that I do. This explains very thoroughly how we can have a large effect, and well, my dog's losing its mind out here. How we can have a large effect and not get statistical significance, because if the null hypothesis is true, I'm sorry, excuse me. If the null, I'm distracted by the dog. If the null hypothesis is false, then we only have a 0.12 probability of rejecting it. So, you know, that's not cool. That's way too low. We need to get our power up around 0.80.